is part 2 of Cosets and Lagrange. We're going to look at the theorems, and we're going to have students describe the theorem and the proof and explain parts that we would need further explanation for. We're going to start with candidate number 1.
So the first element of theorem 26, the cardinality of a left coset of H equals the cardinality of H. You can see in the proof here how that they start essentially with just relating two elements of H together, and then they take out the x with the inverses to get the elements, and then they get a 1-to-1. So like essentially this doesn't matter too much. So they're 1-to-1. So the cardinality is essentially how many elements there are within the group. So what this proof is saying is that x of h has just as many elements in that group as h does. I think that's what it's saying.
With the two h's, and then how was it that you were able to do the inverse, multiply by the inverse?
Well,
I mean, why were you able to do that? H is a what?
It's a, I don't know, group?
Group, yeah.
Okay.
It's a group, and that's one of the elements of being a group is that you have
Has an inverse.
So that's why they were able to multiply by left side x inverse both sides to turn that into E, and we know E exists because E is also a ramification of it.
Mm-hmm.
Good. And what does, two quick things here. So cardinality was what again? What was cardinality?
Cardinality is the number of elements in a group.
And then what do those absolute value things mean?
I don't know.
Anybody? How many in a group? That's the cardinality.
Okay.
So. Thank you. And that was cardinality is the number of those, and that's what that little absolute value. Next one, supposing H is a subgroup of G, X, Y are in G. Next, we're going to do property number 2.
All right. So this property states that X times H will equal H if and only if X is an element of H. So scroll down here and look at the proof. So this is pretty straightforward. So if X times H equals H, then you could say X lowercase h is an element of H, is an element of uppercase H. Therefore, X times E, the identity, will also have to be an element of H since E is an element of H. And E here is the identity of G. Therefore, X will be an element of H. And then you have to prove the converse because it's if and only if. So then we get to, if X is an element of uppercase H, then X times H will equal X star, where H is an element of H. But H is closed under star, so that means that X star H is an element of H for all H is an element of H, which is all lowercase h. Then you know that X times H is a subset of H, and you know that from what Gavin just proved. Also, for H is an element of H, you have to consider the inverse. So the inverse of X star H will equal H because X is an element of H. X inverse has to be an element of H because it is a group. Then you keep going with that, and you say that X star X inverse star H is an element of XH, and you can, because it's associative, you can then redistribute, and you say X star X inverse star H is an element of XH, which then means that E star H is an element of XH, and H is an element of XH. Therefore, H is a subset of XH. We already proved up here that XH is a subset of H. which then means that H is, because H is an element of H, and they're both subsets of each other, they are equal.
Thank you. That ties in really well with what we did a couple chapters ago. And again, we can say that X inverse can be introduced because H is a group, and it has inverse, and it has an identity. Next, we have 3.
All right, so this third theorem states that for xh equal yh, x inverse times y has to be an element of h. And so for the proof, they set xh equal to yh and then multiply by the inverse of x on the left, and you know the inverse exists because x is an element of a group. And so then on the left side, when you have x inverse star x, you know that it equals e, and eh is going to be h because anything times an identity is going to be itself. And on the right side, you can separate the x inverse star y from h because it's associative since it's a group. And then as we saw from the theorem 2, since x inverse star y, h equals h, x inverse star y has to be an element of h.
Is that homomorphic that we had? Is that what they said for homomorphic? Or am I misspeaking? With x inverse star y. That was AB inverse, yeah. But you said that this is from part 2.
Yeah.
So if we go back to part 2, yeah, xh equals h. So then for 3, good. Next, number 4.
Trying to prove that xh intersect yh is equal to either xh or the null set. So how we approach that is we first say xh and yh is x star h1 and y star h2. So then we can say that h1 is equal to the inverse of x times y times h2 because we just multiply by the inverse. And then we can divide, or we can, inverse h2. So we get h1 times h2 inverse equals x inverse star y. And now, yeah, so we know that x inverse and star y is an element of h because of what we've been doing in the past proofs. And h1 and h2 are both an element of h and also have inverses, so therefore they're part of h. And we just proved from theorem 3 that xh is equal to yh, so yay. So therefore, xh intersect yh is equal to xh, because everything because xh and yh are the same thing, therefore anything intersect itself is equal to either side, which is xh. So, yeah, either xh intersect yh is equal to xh, or xh intersect yh is equal to null, because of that, I suppose. It just supposes it.
One of the possibilities.
Yes.
So they either
Right.
at all, or else they intersect with xh.
Right.
All right, 2 more to go. Here's number 5.
So this one is just really straightforward from the previous couple proofs we've done, and it says that the left coset of H, which is a subgroup of G, the only left coset of H, which is a subgroup of G, is H itself. And the reason for that is that to be a subgroup, it has to contain the identity, and from Oliver's proof, we learned that XH is equal to YH if and only if XH and YH are equal, which means that to contain the identity element, XH has to be equal to H, essentially, which means that the only possible left coset of group G. Oh, it has to be H itself. Right.
Good. And then number 6.
Do I have to use this?
Yes.
I do have to? Okay. Do I like put it around my neck? Alright. Wait, can I have some more space to write? Because I want to write.
Do whatever you want.
How do I move it down?
I got you. I got you covered.
Okay.
There you go.
Okay, I guess I'll just write on top then. Okay, there we go. All right. Okay, so basically what this starts with is that so H is a subgroup of G, or like H, which the operation is a subgroup of G. So that means that E, or like the E is an element of H, and that E of H is an element of H because it's a group since it's a subgroup, and that and E of H is equal to E of G since H is a subgroup of G. So then when you're doing the cosets and you have G of H equals, or yep, that. When you do that each time, then E of H is going to be an element of, you're doing it for each H. So like for when you're taking that, then like for each one you're going to do E times whatever element of G you're using that time. So that means that each time you do it, you're going to have that element of G that you're using inside the coset. So when you do it when you get all the cosets, then you're going to get all of the elements of G. So then that means when you take the union of all the cosets, then all the elements of G are going to be in it. So you get G.
All right. So, and then they had well, they didn't have a proof of that. They just said,
They just say that. Well, this is what I was talking about, but I wanted to talk about the subgroup thing because they didn't talk about that since like you have the identity of H is the same as the identity of G, so H is the subgroup of G.
so summing this up, what would you say the main idea is?
The main idea is if you take the union of all the cosets, you get G.
Perfect. And how about 7?
Okay, so basically, if H is a subgroup of G, then order H is a factor of order G. So in the proof, it just labeled order H as M, order G as N, and by theorem 26, it labeled H as M, and yeah. So basically what this means is that if G, order G is equal to N, then R, which is a factor, times M will result in N equals RM, which basically means that order G over order H is equal to the number of cosets. Yeah.
And they're using N or M for that?
They're using R.
R, okay.
With cosets.
Yeah.
And you have G equals N, and then H equals M, and then you can multiply across. And it's not
Right. Next, Elliot.
First wrote this. So this is a corollary for the Lagrange theorem, and it says the order of an element of a finite group is a factor of the order of the group. You don't like that? Okay. So we're gonna let G and star be the group of order n, and then we're gonna get a subgroup with the cyclic generator H, and we're gonna call the group H. And so like the whole point of it is there is a cyclic generator for it. So the order of the subgroup H is the same as the order of the cyclic generator, lowercase h, because that's like the definition of the cyclic generator. And we're going to let that equal m. And then by the Lagrange theorem, we got this stuff here, where the order of the subgroup of H is a factor of the order of the group of G. And so, therefore, since the order of
big H is the same as the order of little h, then the order of the supergroup is if it's a product of some number R, which is the number of cosets of H with G, such that yeah, I'm not sure where I'm going. So we end up here with where R is the number of cosets again. H is, or this absolute H, that's an order of the H, which is a cyclic generator for the group H under star for the subgroup G.
So G and H are multiples of each other, and cyclic generator and G are.
Yeah, that's pretty much it. Okay.
Okay, so um uh so for this one, this is for any prime number, for any positive prime number up to isomorphism, there is one group of order n. So we can say that for any positive integer, the integers of that residual class and then addition modulo n is going to be a cyclic group of order n. So then if G is a group and the order of G is prime, then 1 and n, which is the order of G, are the only factors of n. So by the first corollary, each non-identity element has order n as well. And then for any element of G that isn't the identity element, the order of that is equal to the order of that as a generator, which is equal to n, which is equal to the order of G, as we set up here. And then, so G equals the generator G, which is this here. And then, so G has to be a cyclic group. And that means that this is the only group that fulfills this. So yeah.
All right, we're not quite done yet. Now what we're going to do is I'm going to have everybody come up to the board, and you're going to give me a 10-second overview of what your property is and when you would use it. And it'll be 10 to 20 seconds, but I'm going to give you some time to think about it first.
So this part is essentially the left coset of H has just as many elements as the regular group of H.
Just say what property.
Property 1 of theorem 26.
Property 2 of theorem 26 is if is x times h equals h if and only if x is an element of h. So that can either tell you that can be used to find out if x is an element of h just by multiplying it by the set.
Theorem 3 is that xh equals yh only if x inverse y is also an element of h, which makes it useful in proofs or proving other properties of the theorem.
Yeah, similarly, if xh is equal to yh, then x-intercept, or xh-intercept yh is equal to xh because they're equal. And if x inverse y is not an element of h, then xh intersect yh is equal to the null set of nothing. So that's also useful in proofs and for showing for proving that things are equal or that they do not exist at all, basically.
All right, so this is number 5 of 26, and it says that assuming H is a subgroup of G, the only left coset of H, which is also a subgroup of G, is H itself, and that is useful in if you want to disprove that some set is a subgroup of G. You can do it by showing that it is a coset of another known subgroup of G.
Okay, so for this one, if you take the union of all of the left cosets of H, then you just get G, and H is a subgroup of G, so that's why that works, since the identity of G is an element of H.
So you have H is a subgroup of finite group G, and then the order of H is a factor order of G. So basically, the equation is n equals Rm.
So the order of an element of a finite group is a factor of the order of the group. It's part of the Lagrange theorem. I'm pretty sure it's only useful if you have an element and you have a group. It's like not an element of the group. So.
And then if a number is a prime number, then there's only one group that has the same that order, because if you have that number, then if the number is prime, then the only two factors of it are 1 and n. And so it makes it so that there can only be one group.
Thank you, class.